If you've ever done integration by parts, you know sometimes there's questions that can really get you stuck, and that's the purpose of this video, is to show you why you're currently sucking at integration by parts and how to change that to make sure that you suck less. And usually this boils down to two specific mistakes. So what are the mistakes? You probably guessed it by now. It's picking the wrong value for u in v in the uv minus integral v du equation. It's either that, or you're not properly integrating the identities for 1 over x squared plus a squared and its kind of variance. These are the key mistakes that often crop up. Alright, so now to take a very basic example to illustrate this point, we're going to be using the integral of e to the x dx, right? So over here, we're going to say, well, we don't actually know what u and v should be, so let's just make u equal e to the x, right? Therefore du is equal to e to the x dx. Let dv by dx equal x. dv is therefore going to equal x dx. Okay, so v is going to equal x squared over 2, right? So if we know that uv, let's feed u, applying that, we therefore get e to the x squared over 2 minus the integral v du. Now, as you can see, we're in an even worse place than where we started, right? So obviously here, having a value for u, just randomly picking a value for u and a random value for v, doesn't really work in our favor. So then, what's the solution? What's the solution to this u-v problem? Like, how do you pick the right value for u and v? Well, the solution is Lie8, right? It's similar to BODMAS except for integration by parts, and it basically lays out the structure you must follow when calculating an integral by parts, where logarithms are at the top, right? So you're going to pick u for logarithms every single time, and exponential functions at the bottom. Okay, meaning that if you've exhausted everything else, then only then are you going to pick exponential functions as u, right? So how would we solve the previous question with this new guide? Alright guys, now using Lie8, how do we solve this problem? Right, so remember Liate, and we've got a because we've got x, and we've got e because we've got an exponential. Okay, so a corresponds to x, and e corresponds to the exponential e of x. So what do we say? Well, remember integral, we're going to say uv minus v du, right? Therefore, what's u? Well, we're going to make a u equal to x. Okay. We'll say let dv by dx equal ex. dv is equal to ex dx. So v is equal to ex, right? So then uv minus the integral v du. Okay. What do we get? Well, we get xex minus the integral of e to the x, and then here du is equal to dx, so we've just got dx here. And as you can see, that's made things so much more simple. So what we've got then is e to xe to the x minus e to the x plus c, okay? And that's going to be your final answer there. So evidently this is a very efficient way to solve this problem. Alright, so now we have a scenario where you have to do it twice, right? So using Lie8, right, what comes first? Algebra. What comes second? E. Right, so therefore let you got x squared, therefore du is equal to 2x dx. We say let dv by dx equal e to 3x. Therefore v is going to equal a third e to the 3x, right? Brilliant. So now we can say, well, uv minus the integral v du, we get x squared e to 3x over 3 minus the integral of v du. Shove the third there. Du is equal to 2x dx. Okay, so therefore we've got x squared to 3x over 3 minus a third, actually 2/3 of x e3x dx. Okay. Now from here we're going to say, right, focusing in on this, let u equal x, so du is equal to dx, let dv over dx equal e to the 3x. Okay, which means that therefore dv is equal to e to the 3x dx, and v is equal to, again, a third e to the 3x. And so uv minus v du gives us x e3x over 3 minus the integral third 3 du, and du is equal to dx x e3x over 3 minus a third. Okay, and that's actually going to become a ninth now because we divide by 3, right? So where do we take it from here? So this here is going to equal this integral. So what we've got is x squared e 3x over 3 minus 2 over 3. Copy this, paste it here. Right. And so we get x squared e to the 3x over 3 minus 2 e3x x over 9 minus 2e to the 3x over 27. So that should be plus, actually, and then plus c on the end. Okay, and that, guys, is going to be the final answer to that trig identity, right? So just to recap there, again, it's all about lie 8. So 8 at the top, put it there, e's at the bottom, so we make that dv. Very simple. That helps us to solve this problem, no issues. Alright, guys, so now we've got a trigonometric example where we've got the integral of x sine x dx, right? So how does it work in this context? Well, it's going to work exactly the same. Again, layouts. Okay. That should be a t, sorry. So in this example, we've got a over here, right? And we've got t over here. Now this a corresponds to x, obviously, and the t corresponds for trigonometry to sine x, right? And so in this example, we're going to say, well, let u equal x, so therefore du is equal to dx. Okay, so let dv by dx equal sine x, therefore dv is equal to sine x dx, and therefore v equals what? well, v is going to equal negative cos x. Okay, so uv minus v du. Where do we go from here? Well, we've therefore got negative x cos x here minus the integral of minus cos x dx, and therefore we've got negative x cos x plus the integral of cos x dx. So as you can see, things have simplified a lot, and therefore from here we get negative x cos x plus it's going to turn to negative minus sine x plus c. Actually no, sorry, plus sine x plus c. Okay, and that's going to be the final answer to that question. Now imagine if we did it the other way around. If we made u, okay, if we made u equal to sine x, okay, then du is equal to cos x dx, so dv by dx is equal to x. Okay, so v would have been x squared over 2. Plugging these into this would have been much more of a pain. So what this has done, lie 8, it's simplified things way more for us. Alright, now what about a situation like this? Okay, we can apply lie 8, and when we apply lie 8, what we got is we've got algebra here, exponential here. The algebra is going to be here for t3, obviously. Exponential is going to be et squared. So therefore, let u equal t3 du is therefore just going to equal 3t squared dt, right? But dv by dt equals e to the t squared. And so as you can see, we've got a bit of a tricky one here because we can't actually evaluate this, okay, to find v. So what do? Well, in a situation like that, what we need to do is we're going to say, look, let's make u equal t squared, right? Which means that du is equal to 2t dt. Simple enough. Let's make dv by dt equal t squared. Okay. Again, relatively simple enough there. So we can say from here that, okay, v is going to equal the integral of t squared dt. Okay, and in this scenario, what can we say? Well, if we do that, we can say, okay, well, let u equal t squared. But du is equal to 2t, which means that half du is equal to t dt. Okay, so therefore half du is equal to 2 dt here. So t dt, sorry. So using that information, let's bring it down. Okay, v is therefore going to equal e to the u, our new integral here, half e to the u du. Okay, and so what we get there is a half of e to the t squared altogether when we plug back in. So therefore, altogether, what do we get? So altogether what we get is uv. Again, don't get confused, I've made this a separate substitution. Okay, but altogether here I've said, well, uv, so that's half e to the t squared, okay, times t squared minus v to u, integral of half t squared, and du is equal to 2t du, 2t dt. Right, and so what we get then is half t squared e to the t squared minus a half e to the t squared plus c. Okay, and that's your final answer. So in this scenario, we just have to break it down a little bit further and use substitution alongside integration by parts in order to get the final answer. So in this scenario, it's not perfect science, but it still has helped us out. And in the next episode, what I'm going to do is I'm going to go through the trigonometric inverses and how those fit in to all this. That common mistake.